continuity and we talk about derivatives, we have a kind of a definition here about differentiability and continuity. It says if f is differentiable at x equals c, then f is continuous at x equals c. So basically, differentiability implies continuity. If it's differentiable, then it's continuous. But in the opposite way, continuity does not imply differentiability. Let's actually see that in action. So here we have a continuous function, the absolute value of x minus 1, right? This is continuous here, but if I actually graph the derivative, my derivative is going to look like an open circle at 1, negative 1 going to the left, and an open circle at 1, 1 going to the right. So f of x is not differentiable at x equals 1. This says differentiable, not very well, but it does say that. Because our limit as x approaches 1 from the left is equal to negative 1, and our limit as x approaches 1 from the right, that's equal to 1. These are not equal, so the limit does not exist. So there's no derivative at x equals 1. So where is a function differentiable? Well, let's look at some examples here. We have this graph, f of x equals x plus 3 to the 2/3 power, and we have what looks like a cusp here at negative 3. So it comes down and then it goes up. So we can say that this is differentiable from negative infinity to negative 3, and then again uniting from negative 3 to infinity. Now, if we look here, I'm going to just tell you that this point here is negative radical 5, 0, and this point here is radical 5, 0. So where is this differentiable? Well, we actually have this as differentiable in 3 places, from negative infinity to negative radical 5, then again from negative radical 5 to radical 5, and again from radical 5 to infinity. But actually at negative radical 5 and radical 5, it's not differentiable because we have that kind of sharp point there, right? So we want to find all the values of x for which the function is differentiable. We're given h of x equals x plus 1 squared when x is less than or equal to 0, 2x plus 1 when 0 is less than x is less than 3, and 4 minus x squared when x is greater than or equal to 3. Well, we need to first investigate what is happening kind of at these breakpoints, right? So I'm going to say x plus 1 squared is equal to 2x plus 1, and this I'm going to do when x equals 0. So I substitute in 0 here. I'm going to get 1 squared is equal to 1, which is just 1 equals to 1. Good, it's differentiable there. Now here I'm going to do 2x plus 1 is equal to 4 minus x quantity squared when x equals 3. So I substitute in 3 for x, so I'm going to get 6 plus 1 is equal to 4 minus 3 squared. So I get 7 is equal to 1 squared. That's not true. 7 is not equal to 1. So it's not differentiable at 3. So this graph is actually differentiable from negative infinity to 3, and then again from 3 to infinity. Hopefully that makes sense. Let's do 2 more examples. We want to find all the values of a constant a where the function is continuous over all the reals. Well, we've done this kind of work before. Basically what we're going to do, we're going to have ax squared minus x is equal to 2a when x is equal to 3. So I substitute in 3 here. So I get 9a minus 3 is equal to 2a, right? So then I have 7a is equal to 3, so a is equal to 3/7. And I'm going to rewrite these here. So now I've got 3/7 x squared minus x when x is less than 3, and 2 times 3/7 is going to be 6/7, right? 6/7 when x is greater than or equal to 3. So we found our value, but we need to actually verify that this is true. So we're asking ourselves, the limit as x approaches 3 from the left, is it equal to the limit as x approaches 3 from the right? And I should be writing f of x's here. I did not do that earlier. That is a mistake. So the limit as it approaches 3 from the left, we're going to have 3/7 x squared minus x. Does it equal 6/7? Well, if I substitute in 3 from the left, I'm going to get 3/7 times 9 minus 3. Does that equal 6/7? I kind of wrote that weird. But it looks like we're going to get 27 divided by 7 minus 3. If I calculate, I get 6/7 equals 6/7. So this is true. We actually found a constant that works. And finally, one last example. We want to show algebraically, using the alternate form of the derivative, why g of x is not differentiable at x equals 1. So our target value here is that x equals 1. So we want to find the limit as x approaches 1 from the right of f of x. We're going to do that first. So that's going to be our limit as x approaches 1 from the right of x minus f of 1 over x minus 1. This is where we're coming from the left. This is where we're coming from the right. I started with the right first. It really doesn't matter what you do. And again, this is the limit as x approaches 1 from the right of x minus 1 over x minus 1, which is all just going to simplify down to 1. Okay, so far so good. Now we're going to find our limit as x approaches 1 from the left of f of x. Well, that's going to be the limit as x approaches 1 from the left of x squared minus f of 1 over x minus 1. So that's going to be the limit as x approaches 1 from the left of x squared minus 1 over x minus 1, which I can factor this. So that's the limit x approaches 1 from the left of x minus 1 times x plus 1. These x minus 1's cancel out. So now I have the limit as x approaches 1 from the left of x plus 1, which is equal to 1 plus 1 is 2. So it looks like we have we don't have continuity there. It's not differentiable. So it's not differentiable at x equals 1, right? Because the limit as x approaches 1 from the right of f of x does not equal the limit as x approaches 1 from the left of f of x. All right, any questions? Leave them in the comments. In our next video, we're going to start actually doing some fun differentiation, really kind of get into it. All right, see you in class. Bye.